Okay, so we had a little bit of a short history on the people that were key to the development of calculus, a little bit of their personalities, some of the interesting aspects about the early mathematicians who developed calculus, which was revolutionary mathematics that really led to the scientific revolution. The scientific method and this brand new tool of calculus advanced knowledge of the universe to an unimaginable extent, to the point where physicists had, in 200 years, felt that they had learned just about all there was to learn in the universe until Einstein came into the picture. But now we're going to take a look at integration, and that's all we're going to be doing from here on in for a long time. We're going to look at some of the fundamental integrals, how they're derived, the solutions of the integrals are derived, and for the next 40 or so minutes we're going to show the technique that is used for deriving many of the integrals. And naturally it involves differentiation, because integration is the inverse or the opposite of taking a derivative. So it's an interesting approach. Of course, there are other approaches and methods for coming up with the derivatives, and we'll be looking at these different methods of integration, as well as substitutions and things like that. In fact, to some extent, we even do substitution in the integrals that we do in this set today. So with that, we'll move on, and here's some elementary integrations that will start us off, and we'll be doing lots and lots of integrations. And even the sad thing is that as many integrals that we can take, there are far many more circumstances where the integral can't be found than can be found. So it becomes a trick of being able to find a way around something to find the integral. So anyway, with that, we'll move forward, and I hope this is an informative video to you. Our first, we're going to start with, and it's pretty arbitrary, we're going to start with f of x is equal to ln x and we're going to say dx of f of x is equal to dx ln of x. But we also found when we did derivatives that dx ln of x is equal to 1 over x. So if we multiply across by dx, we have d ln x equals 1 on x dx. When I say ln, that's the natural log of x. But it's true for any log. All logs are related, as we had seen when we dealt with logarithms. Now, if we integrate, we get d ln x equals the integral of 1 over x dx. And this is simply ln x, and this we just keep as the integral of 1 over x dx, and we just swap sides. Oh, just a minute, I don't like that. Okay. 1 over x dx equals ln x plus c. It's not a definite integral, so that's one of our integrations. And we're going to move through several more like that. So we're going to close this and open up a new. Now we're going to move on to the next one. We say f of x equals x to the n plus 1, and we say dx of f of x is equal to dx x to the n plus 1, and this is dx of f of x is equal to n plus 1 over x to the n plus 1 minus 1. So this is n plus 1 x to the n, and so that's our derivative, dx of f of x. And so if we multiply across, we got d f of x, d dx of f of x, but that's x to the n plus 1 equals n plus 1 x to the n. And we multiply across, we got d of x, whoops, made a mistake, d to the, let's see, n plus 1 equals n plus 1 x to the n dx. This is just x to the n plus 1 equals n plus 1 x to the n dx. So if we have swap sides, we have n plus 1 x to the n dx equals x to the n plus 1, or we could leave it like this, plus c, or we could have it x to the n dx equals x to the n plus 1 on n plus 1 plus c2. We'll call that c1. And this is our general formula for polynomials, for integrals. So we've done the second one. We're going to fly through a couple. We're going to now look at the next. That one's true for polynomials of any order. For example, let's say we got an integral. This is an example, e.g. we have an integral. We have a x to the n plus b x to the p minus c x to the L dx. Well, according to our formula, that's equal to, well, we can do it term by term, a to the x to the n dx plus b x to the p dx minus c to the x to the L dx. And now we can integrate. We've got a to the x to the n plus 1 on n plus 1 plus b x to the p plus 1 on p plus 1 minus c x to the L plus 1 on L plus 1 plus c. And one way we can determine whether this answer is correct is by taking the derivative. So we're going to say y equals this, and we're going to say dy dx equals d dx times all of these x to the n plus 1 over n plus 1 plus b x to the p plus 1 on p plus 1 minus c x to the L plus 1 on L plus 1 plus c. And now if I take the derivatives of each term, we end up with a times n plus 1 over n plus 1 x to the n plus b p plus 1 x to the p on p plus 1 minus c on x to the L on L plus 1 times L plus 1 plus 0. And in the end, we end up with a x to the n plus b x to the p minus c x to the L. And that happens to be exactly the same as the integrand. This is the integrand of the integral. And so they're the same. So when we take the derivative and we end up with the same thing, we've been able to check our work. And it's always good to check your work to make sure that you haven't done anything incorrectly. So that was an example of a derivative of a polynomial. The next one is an interesting one. We got y equals e to the x, and dy dx equals e to the x. And so we multiply across by dx, and we got dy equals e to the x dx. And we do our integral. Dy equals the integral of e to the x dx. And that is y equals the integral of e to the x dx. But what was y? Y was e to the x. So we have e to the x equals the integral of e to the x. And that makes sense because the derivative going down is e to the x. Going back up, it's going to be the same. So just swapping sides, we have e to the x dx is equal to e to the x. And we have another integral. Now we could try something new. Not new, really. Let's try e to the minus x. So we got y equals e to the minus x. dy dx equals minus e to the minus x. So dy equals minus e to the minus x dx. We take our integral. Dy equals minus e to the minus x dx. And this is just y equals minus e to the minus x dx. And we swap it, we substitute. We got e to the minus x equals minus e to the minus x dx. And swap sides, minus e to the minus x dx equals e to the minus x. Or if we take the e to the minus x dx, the minus sign, and multiply by -1 across, we have minus e to the minus x. So here we have another integral. We go, we can draw our little box around that. We're moving through quite a few different integrals. Now, let's take a look at some trigonometric functions. These are always interesting. First off, we have y equals cosine of x. Dy dx equals minus sine of x. And multiplying across by dx, we got dy equals minus sine of x dx. Take the integral, and we got dy equals minus sine of x dx. This is y equals minus sine of x dx. Substitute cosine in there for y. So cosine of x equals minus sine of x dx. And we can bring things across. And whoops, boy, that's a spastic. All right, so we have minus sine of x dx equals cosine of x. That's one way of writing it. Or we can multiply by the minus sign. Let's minus 1 across, and we've got the sine of x dx equals minus cosine of x. So we can look at it both ways. No difference, really. Okay, so that's our first trigonometric function. Close. We'll open up another one for the sine of function. So we have y equals sine of x, and dy dx equals cosine of x. Just want to make sure of something here. I realized that my volume was down when I was making the other recordings. So if we multiply across by dy, by dx, we have dy cosine x dx. And now we take our integral and we go dy equals cosine x dx. This is just y equals cosine x dx. We replace the y with sine of x. Sine of x equals cosine of x dx. Now we swap sides. Cosine x dx equals sine of x. Keep forgetting the constants. When we do these integrals, the constants are there. These are not definite integrals, so the constant must be there. So we close that out, and let's look at a couple of these previous ones that we did. Did we get the constant? Yep, we got the constant there. Did we get it in that one? Yeah, yes, we did. Just want to make sure that I didn't forget anything. This one I think I did. Yep. Remember, there's a constant there, plus c. And we are done with that one. And I think we did the same thing to, whoops, that's the c. And where's our negative? Okay, yes. We forgot the C in that one, so we'll just add that up, add that in, plus C. Make these a little longer. There we go. That's more precise. I just wanted to make sure that we had everything correct. I think we caught them on everything else. Now, let's look at another trigonometric function, which is very common. The three main trigonometric functions, sine, cosine, and tangent. So we're going to say y equals tangent x. But we know that tangent x is the sine of x over the cosine of x. So when we do dy dx, we have dx of sine of x over cosine of x. And we got to do our integration by parts, or not integrate, our differentiation by parts. So we got dy dx is equal to, all right, we have negative sine x cosine of x minus 2 times minus sine of x plus cosine of x over cosine of x. And this is equal to 1 plus sine squared x over cosine squared x. And that's equal to 1 plus tangent squared x. But we know from our identity, cosine squared x plus sine squared x equals 1. And if we divide by cosine, we have 1 plus tangent squared x equals secant squared x. And so what we have here is secant squared x. Now we have dy. If we multiply across by dx, and then we do our integral, and we end up with y equals secant squared x dx. But y is tangent. Let's swap sides first. So we go secant squared x dx equals, and y is tangent x. So that's our integration for the secant squared. So we've already done 3 trigs. We've done a couple of exponents. We looked at polynomials. Let's take a look at what is the sinh function, hyperbolic sign. Let's say y equals sinh x, and that's equal to e to the x minus e to the minus x on 2. Just let me just check that 1 second. I just want to make sure that I didn't screw it up. Okay. Okay, yep, e to the x minus e to the minus x on 2. So we got it correct. I just wanted to make sure that I had my function correct. So dy dx equals d dx of e to the x on 2 minus d to the d dx of e to the minus x on 2, and that's equal to e to the x on 2, and that is plus e to the minus x on 2, and that's equal to, well, we just write that shorthand, and that's equal to cosh x. So we say that dy equals e to the x plus e to the minus x on 2 dx. And we do our integral. And we end up with y equals, and we know what this is. We bring our 1/2 out, and we've got e to the x dx, and we've got plus 1/2 e to the minus x dx, and we have right here y is sinh x equals, well, this is the cosh x dx. And let's work this out. So we have, let's just write this like this, cosh x dx equals sinh x, and we box that in. But let's take this integral all the way. So that's e to the x on 2 minus e to the minus x on 2, and that's e to the x minus e to the minus x on 2, which is sinh x. So we indeed confirmed this formula. So we're able to do that to hyperbolic functions, which are basically exponentials. And we can do that with all of them. But I'm not going to do all of them right at the moment. Let's move on to something a little different. Oh, well, let's take before we move into Newton's laws of motion, we've got a summary here of some of the derivatives or integrations that we've done. And so let's take a look at something else. Let's look at this one. This looks pretty interesting. Make sure okay. So y equals the ln of secant x tan x. Well, let's go back just a minute. Ln of secant x plus tan x, and we go dy dx equals, well, let's say u equals secant x plus tan x, and we go du equals, well, that's equal to 1 over cosine x plus sine x over cos x, and this is equal to minus cos x to the minus 2 times negative sine x plus, and we know this is secant squared x, and this is equal to secant x tangent x secant x plus secant squared x. And so we have, let's go back to here. We're going to say y equals ln of u, and dy dx equals ln d du, or d, d dx of ln u equals 1 over u du dx. And this, if we multiply across by dx, we have dy equals 1 on u du. And I forgot one thing. This is du dx. And so du equals this dx. So we have this y is ln of secant x plus tan x equals 1 over u du, and that's equal to ln of u. Well, that didn't get us anywhere. We're gonna have to rethink this one. Is that the one? Yeah. We're gonna delete that one, and we'll have to take note of that in our let's work this one out. This is interesting because I want to make sure I have this right, and we're gonna have to be careful with this. So we have d. Let's say y equals ln secant x plus tan x, and d dx. Let's see here. Let's say that this is u. Okay, equals secant x plus tan x du dx equals, and this is minus cosine minus 2x sine x, and that's plus, plus this is secant squared x. And so du equals tangent x, tan x, oops, let's get rid of that line, tan x secant x plus secant squared x, and that's du dx. So dy du equals ln, I'm sorry, my mind is wandering a little bit, du ln u, and that's equal to 1 over u du. And this happens to be, u is ln of secant, oh wait a second, u is not that, u is 1 over u is 1 over secant x plus tan x. Du is tan x secant x plus secant squared x. And so dx so dy why isn't that writing? dy du dx. This is not very neat. Let's see what we got. dy du dx equals, now this is, let's pull the secant out. We got tangent x plus secant x on tangent x plus secant x times secant x. So this is equal, dx equals secant x dx dy dx. I got something close, but not entirely. So we're going to have to see du dx. Hello?
Hi, Peter Jessica, please?
This is he. Yike. It's pronounced yike.
This is Lisa over in scheduling.
Let's say we got y equals the natural log of secant x plus tangent x. And that's going to be hard to take the derivative. So we use substitution. We say u equals secant x plus tan x. And then du dx is equal to, now this is 1 over the cosine, so that is minus cosine minus 2x times minus sine x. And we know what the tangent is. We've just done that one, so that's secant squared x. And this is equal to tan x secant x plus secant squared x. There we go. And so we have y equals ln u, and we got dy du equals 1 over u du. And that du dx actually dx. And so dy du dx is equal to 1 over u du dx, which is this result right there. So we end up with 1 over u, which is secant x plus tan x, and we have tan x plus secant x and secant x. These cancel, and dy dx is equal to secant x. Neat little trick there. So dy equals secant x dx, and we do our little integration, and we've got y equals the integration of secant x dx, and y is the ln of x. So let's move this over here. Secant x dx equals the ln of secant x plus tan x plus c. And that is pretty neat. That is a really neat integration. And so, there we go. Not a very good square box. I'm going to erase the extraneous stuff here. Alrighty. And let's just improve our box a little bit, and we got our result. That is pretty neat. I really think that's neat. That's a pretty cool result. So that's a good one. That's a really cool one. So we're going to close out that project, and we're going to add another one. I think that is so neat. You know, what you can do. Okay, so let's look at one more integration. Let's say that dy dx is equal to 1 over x plus 5. And we're given find y is equal to the integral of 1 over x plus 5 dx. Well, we know what 1 over u du is. That's the ln of u. We worked that out in a previous problem. So why don't we try a substitution? We say z equals x plus 5 dz equals dx. So we have y, and here we're going to go, I don't know why my pen's not working. Y equals 1 over z dz. And here we have y equals ln z plus c. And we have ln of x plus 5 plus c. So that's what our result is, and that is the result. Now, if we look at another example that we're given, let's say we're given this integration that we have 1/3 3 dx. Let's see if this is the problem. 3 dx over 3x plus 2. All right, so we can say that u equals 3x plus 2 and du equals 3 dx. So dx we've got that right there. So we have 1/3 u du. So we got 1 over u du, and that's equal to 1/3 ln u plus c, and we got 1/3 ln 3x plus 2 plus c. And that's the solution to this. We can continue on for a long time with this. Let's look at a slightly harder problem, and then we'll close out these. We'll close out for today. Okay, so we are given y. Whoops, I shouldn't. I used the heavier pencil. Y equals 1/2 2x dx on x squared plus 3. So let's try a substitution. U equals x squared plus 3 du equals 2x dx. And it seems like we have that in the integrand. So we have 1/2 1 over u du, and that again is 1/2 ln u plus c, and that turns out, when we go back to the original variable, x squared plus 3 plus c. And that is the answer.